Hi, this is Bae. In this video, I am presenting the row-rank approximation-based approach for better forecasting future trajectories. The goal of predicting human trajectories is to infer socially acceptable paths based on previous steps. This is an essential subtask for many applications, such as self-driving cars, delivery bots, urban development plans, robot navigation systems, and surveillance systems. To predict the future paths, the predictor model first observes all the pedestrians in a scene. By observing the past 8 frames, checking interactions between pedestrians, model predict the next 12 frames of trajectories. However, predicting the future paths in real life is still a complex problem. One of the most significant issues is that people don't just go straight. People choose behavior patterns through their inherent decisions at every moment, but it is difficult for the model to know that. Furthermore, these predictions are made in the world coordinate systems, and the time series positions are generated by the predictor. However, this can result in a vast amount of raw data to process. The more pedestrians there are, the more challenging it can be for the model to extract meaningful features from this plethora of information. However, what's interesting here is that all the methodologies so far have used this approach. Going back a little bit in time, before the advancement of deep learning, various methods were used to extract representative vectors from raw data. We can generate face image using 7 basis image sets, we can detect face using 5 filters, and we can cluster words within 20 topics. Then a topic arises here. Can it apply this dimensionality reduction methodology to the trajectory prediction task as well? In fact, the answer is close to us. In such video games, we can control each movement with various combinations of arrow keys. Inspired by this, instead of using all the raw data, we try to use the representative patterns. First of all, we start from the raw time series coordinate sequences. Compared to the existing approaches, we first stacked all the trajectories included in the training set and perform singular value decomposition. By doing this, we obtain eigenvectors equal in number to the dataset dimensions. Due to the characteristics of SVD, these eigenvectors are arranged in order of importance. For example, since most pedestrians move in a straight line, the straight path appears first, followed by the vectors representing various types of paths. As we go further down, the frequency increases, representing not macroscopic movements but microscopic noise. We employ the top K approximations to use only the 6 eigenvectors. Even with such a small number of eigenvectors, we can sufficiently cover various cases such as straight turn left, deceleration, and complex paths through a linear combination with coefficients. Here, each coefficient determines how much a corresponding eigenvectors affect a pedestrian path. For the next step, we define transformation between two spaces by matrix multiplication with eigenvectors. By defining transformation to and from this newly defined descriptor space, we can freely convert the information for perception and prediction. Using these operators, we measure the approximation error to check how accurate the EigenTrajectory is. Compared to the parametric curve models, our descriptor can much more accurately approximate a pedestrian's path, even with fewer dimensions. Using this brand new EigenTrajectory space, we now can predict the future trajectories. The only difference between our model and the usual one is that the model is working in our new EigenTrajectory space instead of the traditional Euclidean space. The cool part is you don't have to change anything else in the existing model to use in this new space, so it's super easy to just plug it in. This is the prediction results of our trajectory prediction results. Although the most predictors use the same baseline model, the predictions made in our EigenTrajectory space are much more accurate and looks much more natural than those made in traditional Euclidean space, which looks noisy and don't align with human dynamics. Thank you for your interest in our work. Our codes are available online.